Hello everyone, good evening. My name is Nehel and welcome to the stream by OneClass. Today we'll be going over a few physics questions. These would be ranged from anywhere from high school to university level physics questions, and we'll be solving around 10 to 15 questions today. Just a little bit of background about myself. As I said, my name is Nehel. I graduated from University of Waterloo in 2018. I went there to study mechanical engineering. I've completed over 6 core terms and I've been working for the past 2 years as well. I will actually be starting my master's degree as of next week from University of Toronto, and I'm also doing that in mechanical engineering. All right, without further ado, let's get into and solve some physics questions. Okay. So question number one is a pulley-based question. The question says the system shown in the figure is initially at rest when the lower string is cut. Ignore air resistance and friction between the rope and the pulley. Find the speed of the 2 kg mass when it is momentarily at the same height as the 3 kg mass. Okay, let me just copy this image over so we can see it as we solve the question. Okay, so this system is initially at rest, and we cut this string over here, which has another mass, which makes this whole system move. One thing to note here is that since it's attached by one string, and we should be familiar with the principle of conservation of string, the distance this 3 kg block moves down is the same distance that this 2 kg block would move up. So the first part is find the speed of the 2 kg mass when it is momentarily at the same height as 3 kg mass. So again, if we apply the principle of conservation of string, we know that these would be at the same height when they are at this middle point. So if they're initially 1 meter apart, they would be at the same height when both the masses meet at the middle point, which is they travel 0.5 meters. Now, to find the speed, we know the distance it travels, so we can use one of the equations of motions. So for part A, we'll use the equation of motion v square minus u square is equals to 2ah. A is the acceleration. U is the initial velocity, which is actually equal to 0. So this goes away, and we are left with v square is equals to 2ah, where v, which is the final velocity, would be equal to under root of 2ah. We know h, since they meet at the middle point, which is here, is 0.5 meters. So h is equals to 0.5 meters. However, we do not know the acceleration. So to calculate the acceleration, we'll have to first draw the free body diagrams of both the two masses and solve for the acceleration. So for the 3 kg mass, we have the mass of the block acting downward mg and the tension acting upward, and the overall system moves in the downward direction ma. Therefore, and let's call it m1. So m1a is equals to, and then this is also m1, m1g minus t. So that's the equation of motion of this body. The way we solve, or the way we prepare these equations of motion is you look at the positive y and the negative y direction in this case, and then you add the ones which are in the positive y, so t, and then the ones in the opposite direction are subtracted, and then you rearrange to get for ma equal to the sum of the forces. And then for the other box, or the other block, which is the 2 kg block, we have the tension acting upward, the mass acting downward, and this block is actually moving upward. Now, it's important to note that the acceleration of the two blocks will be the same. This is again due to the principle of conservation of string. When two masses are attached by the one string and you pull on one end, the other mass will also move at the same speed. And it also says that we have to ignore air resistance and friction. So therefore the acceleration is the same. The equation we get from this is m2a is equals to t minus m2g. So this is equation number 1. This is equation number 2. We don't really need t. We want to solve for acceleration, so we can plug it over here. Let's call this equation A. So what we would do is we would add 1 and 2. 1 plus 2. When we add 1 and 2, what we get is m1a plus m2a is equals to this t and this negative t, when we add them, gets cancelled out, and we're left with m1g minus m2g. Both these terms have m1 common. Sorry, on the right hand side we can take g common, and on the left hand side we can take a common. So we're left with m1 plus m2 is equals to g times m1 minus m2. And then if we rearrange for a, we would get a is equals to g times m1 minus m2 divided by m1 plus m2. Okay, we'll plug in the values. G is equal to 9.8. Mass 1 is 3 kgs. Mass 2 is 2 kgs. And again, mass 1 is 3 kgs. Mass 2 is 2 kgs. So we get 9.8 divided by 5, which is equal to, let's solve that. 9.8 divided by 5 is 1.96. So that's the value for acceleration, meters per second square. So from equation A, we had we had V is equals to square root of 2AH, which would become square root of 2 times 1.96 times h, which was the height, which we know is 0.5. So on solving this, we would get 0.5 square root 1.4. So V is equals to 1.4 meters per second is the solution for part A. For part B, it's asking us to find the speed of the 3 kg mass. So the way you can think of this question is, there's two ways of solving this. One is just by what we discussed earlier, which was that the acceleration of these two is the same because they're connected to the same string and there is no friction. Similarly, since they're connected to the same string, as one block moves down, the other block moves up with the same velocity. Therefore, the velocity of the two blocks has to be the same. But if you were to do it the other way, which is through the equations of motion, you would notice that the equation of motion would be the exact same, which is V is equal to 2AH, even for the 2 kg, even for the 3 kg block. So for 3 kg, the equation is under root of 2AH equals to V, and it's independent of mass. There is no mass involved. Therefore, this is also equals to 1.4 meters per second. Okay, let's keep going. What is the change in kinetic energy of the 2 kg mass? So initial kinetic energy, so delta Ke is equals to K final minus K initial. which is equal to, now K initial is 0 since the object was at rest, so we can say this is 0, and it's only would be equal to K final when kinetic energy is given by the equation of 1/2 m, in this case it's m2 v squared. So this would be equal to delta K E is equals to half 2 times 1.4 square, which is equals to 1.4 square is equal to 1.96. Okay, and then the units would be for energy, so there would be joules. And for part B, we would get what is the change in potential energy for the 3 kg mass. So again, delta K E is equals to K final minus K initial. This is 0 since the object was at rest, so we would get half m1 v square is equals to half times 3 times 1.4 square, which is equal to 0.5 times 3 times v square. V is 1.4, 2.94. Okay, and finally, what's the relationship between your answer A and your answer B? What happens to this relationship is air resistance and friction are not negligible. So the relationship is that they both are the exact same. The speed would be the same. And even when they are not the same, I suspect there should be no change. Yeah. So even when, because the conservation of strings still applies, if you're pulling one end, let's say if you're pulling the 3 kg end by some velocity, the 2 kg end will also be pulled back at the same velocity. So that would still apply. So answer to part E, answer to part E would be part A and B are the same due to conservation of string. Now I'm calling it string, but this essentially means the rope or whatever the connecting medium is. And similarly, the relationship does not change because of conservation of string. Okay, all right, let's review some of these answers. So for the first part, it is correct. We got our acceleration to be 1.96, and then they used that to calculate velocity, which is 1.4 meters per second. For our second part, it's the same again, perfect. For the third part, we got 1.96 joules, and again we got my bad. So the question actually asks for the change in potential energy for this part. So we calculated the change in kinetic energy. So the change in potential energy for, so delta PE is equals to potential energy final minus potential energy initial. Now final potential energy, the way we do this is we define a coordinate system. Okay, so for this block, let's say I define a coordinate system like this, where this is 0 and this is the initial position. So initially, if we define it like this, we are saying initially the body is at height 0, so the initial potential energy is 0. The other way you can do it is if you define the coordinate system instead of that like this. If this is your coordinate system, sorry, y and x, then you're saying that initially the body had some potential energy, but when it falls down to this side, it has no potential energy. So you can do it either way. Let's stick with this because it's very useful in a lot of cases. You'll find out. So with this way, we're saying the initial potential energy is 0. The final potential energy will be mgh. So this is 0. The final is mgh, which is 0.5. So this would be 3 times 9.8 times height, which is 0.5, which is equal to 14.7 joules. So that was correct. Okay. And the part E is also correct. All right. So the solution are correct. All right. Let's go on to the second question. A toy car moves with a constant speed around a circle. When its coordinates are x equal to 0, y equal to 3, its velocity is 6 meters per second in I direction. When it's at x equal to negative 3 meters, y equal to 0, what is its acceleration? Okay, so since it moves around a circle, let's draw a circle. And let's quickly draw a coordinate axis as well. Okay, so initially this object, this car is at point x equal to 0, y equal to 3. So it's somewhere here, and it's moving, and its velocity is strictly along the y-axis or the x-axis. So v is equals to 6 meters per second. Okay. Now it's asking when it is at x equal to negative 3 and y equal to 0, what is its acceleration? So when it's at this point, what is its acceleration? Now you have to note here that the question is specifying that it is constant speed. So constant speed essentially implies that there is no tangential acceleration. So tangential acceleration results from change in speed, whereas centripetal acceleration results from change in direction. So in this case, since we're moving along a circle, we're changing direction at every instance. So we would have centripetal acceleration, but not tangential acceleration. And at this point, our velocity is upwards, but the magnitude is the same. Meters per second, and instead of I, this is J. Okay, so let's write this down. So let me make this bigger so you can clearly see. Since the object moves around the circle with constant speed, there is no tangential acceleration, as it is a resultant of change in speed. On the other hand, since there is change in direction of the velocity, we have centripetal acceleration. Okay, so hopefully That makes it more clear why we don't have tangential acceleration and why we have centripetal acceleration only. So now, since the question is asking for what's the acceleration, all we need to do is plug in the formula for acceleration. AC is equals to v squared over r, where v is the velocity and r is the radius. We are already given the velocity to be 6 meters per second, and the radius from the circle which we drew is 3 meters. So therefore, this is 6 squared over 3 is equals to 36 over 3. It is equal to 12 meters per second squared. Okay, so that's the centripetal acceleration. Let's make sure that that's the same solution. And this is actually very important to note, and I should draw it, that the centripetal acceleration would be always acting towards the center of the circle. So the AC would be acting towards the center at all instances. So at this instance, at this instance, at this instance. Okay. So we get acceleration to be 12 I cap, which is exactly what we got as well. So great explanation, and the answer is correct. Okay, let's jump right into the third question for today. 2200 kg truck traveling north at 34 kilometers per hour turns east and accelerates to this many kilometers per hour. What is the change in truck's kinetic energy? Excuse me. Okay, so we have a truck. Okay, so we have, this is the north, south, east, west. So north, south, east, west. Truck is initially traveling north at 32 kilometers per hour. So initially our truck is traveling north 32 kilometers per hour, which then turns and accelerates to 49 kilometers per hour and starts traveling east. Okay, the question is asking for the change in truck's kinetic energy. So this is a fairly straightforward question, and the way we would solve it is using the formula for kinetic energy. So kinetic energy is equals to half mv squared. It's important to note that I drew this diagram just for a visual representation, but in the actual sense of the question, we don't really mind which direction the truck was going in, because kinetic energy, change in kinetic energy is a scalar quantity. It does not get affected by the direction of motion. So therefore, we can plug in the velocity in this equation as is, and we don't mind if it's north direction or east direction. So therefore, change in kinetic energy is equals to kinetic energy final minus kinetic energy initial, which is equals to half mv2 square minus half mv1 square. So we basically get E equals to half times 2200 whole multiplied by v2, which is 49. 49 square minus 32 square. Okay, so square minus 32 square times 2200 divided by 2. So it's a big number, so we would, actually I just noticed one thing which we do need to do is conversions. So since the unit of energy is in joules, which has the standard units meters per second, we need to convert this as well before we proceed any further. So the conversion is as follows. We go from uh, 32 kilometers per hour. 1 kilometer has 1,000 meters. Oops, it should be the other way. One, let's write down as this. So 1 kilometer has 1,000 meters. 1 hour has 60 minutes, and 1 minute has 60 seconds. Therefore, this 32 kilometers per hour becomes 32 times 10 divided by 36, 8.88 meters per second. And the other quantity, which was 49 kilometers per hour times 10 over 36 is equals to 13.6 meters per second. Okay, so now we can go back in, and our steps were fine. We still need to calculate the change in kinetic energy. However, the units were not. So this would be V2 would be 13.6 square minus 8.8 square. Okay, so from that we get 13.6 square minus 8.8 square times 2200 divided by 2. Since it's a big number, I will now divide the final answer by 1,000. So we get 118,272 joules, or 118.2 kilojoules as the change in kinetic energy. Okay, I'm not sure why there is a bit of a difference, but I think that might have to do with them using additional decimal points. I think one decimal point is usually fine. Okay, so I would say the answer is correct. Okay, let's go on to the next question, question number 4. Okay, so this is based on an inclined plane. 22 kg block slides down a frictionless slope which is at an angle of 20 degrees starting from rest. The time to slide down is t equal to 1.9 seconds. The acceleration of gravity is 9.8. What is the total distance traveled to which the block slides? Okay, it says it's a frictionless slope. Okay, and essentially if something's frictionless, ideally it would keep sliding down, but we are capped by this time t equal to 1.9 seconds, so that's all the duration we can slide down for. So we need to find how much this block slides down given this much time. Okay, so let's copy this diagram over. All right, and let's first write the equation of motion, which would help us solve this. So we're given we are at rest, and we know the time, so we would use s is equals to ut, which is initial velocity, plus half at. I think that's the equation. Yeah, half at squared. Okay, so since the initial velocity is 0, this term goes away, and we're left with half at squared, where a is the acceleration, t is the time. We know that time is equals to 1.9. second, and we need to solve for S. Therefore, the only unknown in this equation is acceleration, which we can solve for if we uh, prepare a free body diagram. So let's make a free body diagram for this. So we have an inclined plane, and we have a block which is at an angle 21 degrees, and this block is 22 kgs. Okay, so we know that. So what I'm going to do is the first force which acts on this is the force of gravity, mg, and there's no friction, so we can ignore that. There's also a normal force which acts on this, which is from the contact with the surface here, and we can resolve this mg components into two components. So we would have the sine component, mg sine of 21 degrees, and we would have the cos components, mg cos of 21 degrees. Okay, if we look at the sum of forces along the surface of the plane, we only have mg sine of 21. Therefore, F is equals to mg sine of 21 degrees, and F is equals to ma is equals to mg sine of 21 degrees. The masses get cancelled out. We're left with A is equals to 9.8 times sine of 21 degrees, which is equal to 3.51. So we get 3.51 meters per second square. And if we plug that back into our equation, which was S is equals to half AT square, we get half times 3.51 times time, which is 1.9. Therefore, this becomes 2.51 times 1.9 square times 0.5. 6.33 meters. Okay, so therefore this block slides down 6.33 meters before it, or in 1.9 seconds. So let's just write that down. The block slides down the inclined plane 6.33 meters in 1.9 seconds. Okay. Alright, so that's the final answer, and they have gotten the same answer as well. So they used the free body diagram. They did not show the free body diagram, which I highly suggest we prepare every time we're solving any box related question. Then we use the equation of motion. Since it's at rest, we get, so the answer is correct. So I'm going to mark this as incorrect because I personally do believe that we need to show the free body diagram every time we do a question like this. Free body diagram of the block in order to better understand how we got the equation A is equals to G sine theta. Okay, so I guess mark it as correct and give them some feedback on it. Alright, next up, question number 5 for today's section. A mass of object 2.5 kg is moving along a straight road in direction pointing 18 degrees north of east. Force whose magnitude is 49 Newton pointing 55 degrees to the west of south acts on the object. What is the magnitude of the parallel and vertical components of this force? Okay, well, let's first draw this scenario. Okay, let's mark down our 4 directions. So north, south, east, and west. So the object is initially moving on a straight line pointing 18 degrees north of east. So the way you think of that is you would be traveling east, but then you go north. So you go 18 degrees north. So this angle is 18 degrees. A force whose magnitude is 47 newtons pointing 55 degrees to the west of south. So again, you are traveling west, but you pull yourself 55 degrees, or you're traveling south, you pull yourself 55 degrees west. So that would look something along the lines of, I don't want to draw it exactly on the same angle, so let's say something like this. This is the force direction, which is 55 degrees. What is the magnitude of the parallel and vertical components of this force? Okay, so the important thing to note here is when you think of a billiards or a pool ball, and if you hit a ball which is already moving, let's say if this ball was moving here, and if you hit it in another direction, it won't travel in the direction you hit it. It will travel in some other direction. Essentially, the reason I'm saying that is we won't use this 55 degrees in order to compute the components. This is actually at an angle of 55 plus 90 plus 18 degrees with respect to the object. That's the force which is being applied, and we would have to use that in order to calculate the forces on the object. So our theta is actually equal to 55 plus 90 plus 18 degrees, which is equal to 163 degrees. Okay, so it's 163 degrees from this point to there. Alright, and parallel and vertical components. Okay, so if you think of this as this, okay, so this would have 2 components. F would have 2 components, which would be F sine 163, which would be equal to 47 times sine of 163, which is 13.7 newtons. And the other component would be F equals to F cos of 163, which is equals to 47 times cosine of 163, which is equals to negative 44.9. Okay, and then okay, so when we resolve this, this would be acting like this. This would be one component like this and one component like this. So the vertical component would be, okay, that makes sense. So this component here is your cos theta, and this component here is your sine theta. So this is the vertical component, and this is the horizontal component. Okay. So again, that's the diagram of this question. You can append this to here to better visualize what it would look like, and then use that to get the angle. You get the same angle, and then use that to resolve the forces like we've done here. So the answers are correct in this case. Okay. All right. Just give me 1 second. Okay. Let's jump into the next question. So that's question 6 for today's session. 4.9 kg ball is dropped from height 10 meters above one end of a uniform bar that pivots at its center. Okay, so let's draw this question as we go along. So there is a bar, and we have a 4.9 kg ball which is dropped. Okay. The bar has a mass of 5.5 kgs and is 7.8 meters in length. If the other end of the bar sits another 5.3 kg balls unattached to the bar, the dropped ball sticks to the bar after collision. How high will the other ball go after the collision? Okay, so we have another ball here which is unattached but sits on the bar, and the first ball is dropped. So this height is given to be 10 meters, and this thing is pivoted about the center. So when this ball gets dropped and it sticks, essentially what happens is the bar rotates and moves downwards, and this end would move up, and this would launch the ball upwards in air. And the overall length is 7.8 meters. So firstly, what we can do is, we know that initially this ball had some potential energy, but it did not have any kinetic energy since it was dropped from, it was dropped. So it was not thrown, it was dropped. So when it hits the bar here, all of its potential energy would be converted into kinetic energy. So therefore we can say that mgh, or let's call it m1, and m2. Okay, so m1gh is equals to half m1 v square, which is the potential energy equal to kinetic energy. So the masses get cancelled out, and we get v is equals to square root of 2 times gh, which is equals to 2 times 9.8 times the height, which is 10, which is equals to times 10, 14. So we get the velocity to be 14 meters per second. This velocity is the velocity with which mass 1 hits the bar. Now we need to translate this velocity and find the velocity for bar 2. That would be the initial velocity with which it's launched up. So to do that, we need to think of the principle of conservation of linear momentum, of angular momentum. So when this block falls here, this falls down with an angular momentum, and when this block is launched up, that goes up and has an angular momentum associated to it as well. So what we can say is that the angular momentum of block 1 would be, or the angular momentum on this bar due to block 1 is equal to angular momentum which this bar would give to block 2. And the equation for angular momentum is given by m1 v1 r is equals to m2 v2 r. R in both the cases are the same because they are both the same distance away from the pivot, so they cancel out. Therefore, we can actually solve for v2 from here. So we will get v2 is equals to m1 over m2 times v1, okay, which is equal to 4.9 over 5.5 times 14. Okay, so this becomes equal to 4.9 times 14 divided by 5.5. 12.47. Which is the velocity of the second block. It's important to know that we were able to use this conservation principle because it says that the first block, when it fell down, it got stuck to the bar. Otherwise, we won't have been able to use the principle. Okay, now with that in mind, and we have the initial velocity of block 2, what we can say is when it goes up, all of its kinetic energy will be converted to potential energy. So what we use for block 1, we're reversing that and saying, oh hey, initially this block has some kinetic energy, but when it goes up, it would all be converted into potential energy. So we can say that for block 2, Ke is equals to potential energy. So kinetic energy is equal to potential energy by the law of conservation of energy. So we can say that half m2 v2 square is equals to m2 gh. The masses get cancelled out, and we're left with h is equals to v2 square over 2g, which is equals to 12.47 squared divided by 2 times 9.8. Okay, squared divided by 2 times 9.8, which is 7.3. Okay, now it's very important to note that this actually makes sense. The reason I say that is if you have a lighter block which is dropped on here and a heavier block is on the other side, and this is dropped from 10 meters in height, the heavier block would actually not go up as much as 10 meters. It would go up a few less smaller distance. So it did go a smaller distance up, which is 7.93 meters. Okay, so let's look at the solution. We solve for v, which is initial v, which is 14. The angular momentums are the same. We calculate v2, which is 12.9. Fairly, maybe I miscalculated it. 4.9 times 14 divided by 5.3. I see. So they actually used. Okay, so this should have been 5.3 because the bar was 5.5 kgs, but the block was actually only 5.3 kgs. So this is 5.3, which makes it 12.9. Okay, so this is indeed 12.9 meters per second. And then for block 2, everything is correct, just we have to replace this quantity to be 12.9 squared. So this is 12.9 squared, and we get the final answer as 12.9 squared divided by 2 times 9.8, which is equal to 8.49. So it went up a bit higher than what we had originally estimated, but as you can see, it still went lesser distance than the initial 10 meters. Okay, so the answer is correct indeed in this case. Okay, let's jump to question number 7. So we have two objects with mass 1 kg and 7 kg, which are connected by a light string that passes over a frictionless pulley. To find the tension, acceleration, and distance each object will move in the first second of motion. Okay. So let's copy this diagram over. We're given the two masses to be 1 and 7 kg. And this is 7 kg. So the first step would be to draw the free body diagrams. Okay, so for the 1 kg block, as you know, the 7 kg is heavier, so the 7 kg block is going to go down, and the 1 kg block will be moving up. So it's moving up with let's call it M1A. Okay, the weight of the block is acting downwards, which is mg, and the tension in the string is actually pulling it upwards, T. Okay, and for the second block, which is the bigger block, we have the weight of the block pulling it down. The tension wants to resist it, so it's pulling it back up, and then the overall motion of the system is downward, so it's M2A. Note again that by the principle of conservation of string, we have the two oscillations to be the same. So A for both the masses is the same because the string, as it moves, pulls them at the same acceleration. Okay, so from this we can write the equation of motion to be M1A is equals to T minus M1G, and then for this one we would get M2A is equals to M2G minus T. Let's call this equation 1 and let's call this equation 2. If we were to add 1 and 2, we would get M1A plus M2A is equals to, the tension would cancel out, and we would be left with M2G minus M1G. From here, we can actually solve for acceleration right away. So we can say that M1 plus M2A is equals to G times M2 minus M1, and acceleration becomes G times M2 minus M1 divided by M2 plus M1, which is equals to 9.8 times M2 is 7, so 7 minus 1 over 7 plus 1. So 9.8 times 6 divided by 8. So we get 7.35 as the acceleration. So 7.35 meters per second squared. Okay, so now that we have the acceleration, we can actually plug this acceleration back into any of these two equations and solve for t. So we say plug A equal to 7.35 meters per second square into equation number 1, and we would get M1, which is equal to 1, so 7.35 times 1 is equals to T minus mg, so m was again 1 times 9.8, Therefore, we get tension is equals to 7.35 plus 9.8 is equals to 17.17 newtons. Okay, so this is actually the solution to part A, and in order to solve part A, we actually found the acceleration as well. So we found the solution of part B as well. So part A, tension is equals to 17.17 Newton. Part B, acceleration is equals to 7.35 meters per second square. Okay, and part C, determine the distance each object would move if in the first second. So for time t equals to 1, how much would it move? So we can use the equation of motion. S is equals to ut plus half at square. Since we know that the initial velocity is 0, this term goes away. We can say S is equals to half of 7.35 times time, which is equal to 1 second, so 1 square. We basically get 7.35 divided by 2, which is 3.675. So both masses would move 3.675 meters in the first second. Okay, let's check the answer. So that's a free-body diagram, which is perfect. We write the equations of motion and then we solve for A, which is correct. We get 7.35 meters per second square. From that, we plug it back into one of the equations and we get the value for T, which is 17.15 Newton, which is correct. Part B was already answered. The distance the mass will move in the first second of the motion, we used the equation of motion. Initial velocity is 0 and we get 3.675 meters. So perfect. So the solution is correct. Okay. I think we're somewhat running out of time. We can actually quickly do this question. This is a fairly straightforward question. Question number 8. Two vectors have magnitudes 10 meters and 15 meters. The angle between them are drawn with their tails at the same point is 65. What is the component of the longer vector along the line of the shorter vector? So we have two vectors which have magnitude 10 and 15 meters. So this is 15 meters and this is 10 meters. The angle between them is 65 degrees. The question asking us for what is the component of the longer vector, which is the 15 meter vector, along the line of the shorter. So if we were to resolve this vector into its two components, we would get that to be 15 sine of 65 degrees and 15 cos of 65 degrees. Therefore, this is the component of the longer vector along the shorter vector. So that is the answer. So 15 cos of 65 degrees is equals to 6.33 meters along the along the shorter vector. Okay, so perfect. This answer is also correct. All right, I think that's it for today's session. Thank you so much for tuning in. This has been Nehel, and If you do like this video, please feel free to like, comment, subscribe. If you have any particular questions related to any subjects, you can check the link or the description below this video. And I hope to hear from you guys soon. Thank you so much and have a good night.